Hello everyone, welcome back to the course of higher surveying. In the last module, that was the introduction to higher surveying, we have discussed one particular case where we said that let us say we have forest of area 40 kilometers by 40 kilometers. In that forest, I want to measure the height of the tree, canopy size, vegetation volume and the diameter of the tree. Now we discussed that whatever techniques we have, can we use these? What we learned in basic surveying. And the first technique, for example, like theodolite, total station, compass, all the things we have used, and we try to find what are their positives and what are their negatives, or what is the pros and cons of each technique. There we realized that even we take techniques like total station or GPS, although they are very accurate, but still they cannot deliver me more than 1 point at a given time. And for that reason we realized that even if I take techniques which give me higher accuracy, but if they are not time efficient, I cannot use for larger areas. Apart from that, if I look for easier techniques like plane table, which is a graphical technique and which is quick also, I can map the things, but still the accuracy has to be compromised. Moreover, all these techniques cannot consider the curvature of the earth, or I need to take some special care for that aspect. Okay, so we realize now that we can do many things with the classical surveying techniques, but still these techniques have a lot of limitations, and hence we discussed and we concluded that we need some better techniques, and that is why we developed the appropriate context of this course called higher surveying. And now in the same series of lectures, we are in module 2, where first we need to understand that for a sphere like earth, we need to have some kind of coordinate system and reference frame, which should be quite different from the techniques that we have already learned, like plane table or maybe total station or a GPS. Apart from that, we should first understand for large areas, I need to have some different requirements also. Okay, so let us dive into this module 2, and the first lecture of this module is the understanding reference system, reference frame and coordinate system for earth. Remember that we are trying to define this reference frame, reference system and coordinate system for the earth, and not for a small area of 100 meter by 100 meter, 50 meter by 50 meter and so on. This module contains 3 lectures, and we'll go one by one in a series and we'll connect them, that how are these connected together. Well, so let's start with the first lecture. Okay, so we have already criticized the classical survey technique, but in this classical survey technique there are some aspects that we should first understand in order to modify our concepts. Okay, so what we did in case of classical survey, we did first the planimetric survey, that is what we call two-dimensional survey, and we have created map showing the XY position of different points on the surface of earth. So in this screen, if you see, the terrain has been shown by a green color line where few points are marked. I am trying to measure all points, so basically they are 8 in numbers. So let us say I am trying to measure these 8 points on the surface of the earth and trying to draw a map. So I might have used total station, I might have used theodolite, or I might have used triangulation, trilateration, any technique. And finally I could get the map that is showing the XY position of these 8 points. Okay, so we have projected these 8 points on the map plane, okay, in the planimetric survey. That means we are recording 2D coordinates of these 8 points on the surface of earth, and then we are drawing on the map plane. So this is my map plane, and we have projected these 8 points to indicate the horizontal position XY of these 8 points. Okay, later I did vertical survey, that is a one-dimensional survey, and I collected the heights with respect to equipotential surface. Since I do not have any idea of equipotential surveys, so that's why I took the mean sea level by observing it, the variation of sea level over the period of 19 years, and then I found out what is the mean sea level average over the long period. Okay, then I call that as a 0 level, and with respect to that level I find out the level of other points. So if a point is having its level, that is reduced level, with respect to the zero level or the mean sea level, then we call it benchmark, because benchmark is a point of known elevation. Using the benchmark at a given place, for example in this campus of IIT Guwahati, I assume that there is an equipotential surface that is passing through the benchmark, and I can measure the heights with respect to that equipotential surface. Well, that concept was okay for a small area, and we'll see now why it is not appropriate for a large area or long sites or long distances. So let us see what we have done. So let us see, this is an equipotential level surface, and for these 8 points I have measured the vertical heights of the 8 points from the equipotential surface, and these are the 8 heights we have measured, H1 to H8, right. So then I have created a 3D map by superimposing these heights on the map like this. So I have given elevation to these 8 points from the map, and then I call it is a 3D map. 3D map is showing me the x, y, z, that is xy I obtained from planimetric survey, and the third dimension, that is the height, I obtained from the vertical survey by leveling exercise. In this process, what is the problem? We have to first understand that. And the first problem is, it is not appropriate for large areas. For the large areas, expert of the field of survey call it pseudo 3D survey. Okay, and if I go to the word called pseudo, you will be realizing that pseudo is something that fulfills the characteristics, but still it is not the same. Okay, just recall some movie where an actor has double role. Okay, so the original actor or the original character comes into the movie and he is doing something, and after few minutes of that, the duplicate or the pseudo person replaces him. Both are looking same, but the pseudo person or the duplicate cannot replace exactly the original character, and that is what we call the pseudoness. That means it is fulfilling the characteristics, it is fulfilling the criteria, but still it's not the same, or it is not an appropriate, or it is not exactly the same thing. Okay, so it's kind of replacement. Fine. So what is pseudoness here? And that's more important. Why expert says it is a pseudo survey when I do two-dimensional survey and I perform the 1D survey by leveling, or I superimpose the 1D survey on the 2D survey and I call it's a 3D survey. So here the expert says that first of all the problem is the plane surface is not a reference surface. Plane surface means the map surface. What we call here is map, it is a plane surface because we have projected 8 points on a flat plane. And why did we assume it flat? Because if you remember, we realized that for a long distance like 10 kilometers, if I take the line of sight along the line of collimation, which is horizontal, and if I take the length of the sight along the surface of the earth, if I calculate the difference of the two lengths, the length difference is in millimeters, and hence we said for a long distance like 10 kilometers, if differences are in millimeter, obviously for 100 meter, 200 meters or even 1 kilometer, they will be minimum. And as a result, we said that yes, we can do the planimetric survey by assuming earth as a flat. And that is why we said that our map, which is compiled by a 2D survey, is a plane. So a plane can always represent a map that will contain only two-dimensional x and y coordinates of each and every point on the area of interest. Okay, but we realized later that for a long distance like 10 kilometers, the difference of the vertical height along the line of gravity will be in meters. And we realized that it is quite awkward if I use the concept of flat plane or the earth is horizontal. So then we separated the two surveys. We said that okay, for 2D survey I can assume earth as a flat plane, but for the 1D vertical survey I need to assume it to be a curvilinear. And then we use the concept of equipotential surface, and equipotential surface was replaced by mean sea level. And then we realized, let us say establish some benchmarks, and let us assume equipotential surface is passing through the benchmark. And then we realized that how to calculate the distance in the direction of vertical line. By leveling operation, we have created the observations in the direction of vertical line or gravity line. So the idea is the plane surface is not the equipotential surface, because equipotential surface is curvilinear, although it could be an arbitrary surface also, but still it is a curvilinear, and hence that is the first flaw. Secondly, what happens is the reference surface, which is equipotential surface, is not a plane. So by assuming the height h1 to h8, superimposing on the flat map, I am indirectly committing two mistakes. First, I am assuming that the equipotential level surface, which is curved, is a flat, and secondly, I am saying that the reference surface, which is not flat, I am putting it to flat. Some kind of cyclic problem it is. Especially this approach is okay for a small areas like 100 meter by 100 meter, 200 meter by 200 meter. Let us say you have an apartment, or you want to build an apartment from the ground surface. So apartment could be of size, let's say 50 meter by 50 meter. So this kind of ideas are most appropriate for such small sites. Or even if you want to develop library could be as long as 30 meter by 30 meter, not more than that. For such a small area, this concept of 2D survey and separate 1D survey is most appropriate, and they are applicable, and people have been doing it. But now for a large areas, we should consider two important factors. One is the gravity potential, because on each and every point on the surface of Earth, gravity varies. And remember that we are using the direction of gravity to measure our vertical heights. Okay, and then we should also take the 3D observations simultaneously. That means I should not separate two-dimensional survey and one-dimensional survey at any cost. So if we acquire the 3D data simultaneously, that is x, y, and z, where we also consider the gravity potential of each and every point, that will be the wonderful and the best approach. So let us look into this. So now let's look into the shape of the Earth. So what are the Earth characteristics? Because of that, we want to develop our strategy or methodology so that we can develop a 3D reference system in which we can measure our 3D coordinates simultaneously. This is the surface of the Earth as visible from the satellites. And now if we say that the real shape of the Earth is very irregular and complex, as we can see here, there are some sea, there are some lands, there are some hills, there are some big mountains, and so on. Well, if you see that Earth's surface is close to the oblate spheroid, what does it mean? I am showing you a red mark here. Red mark shows the diameter of the Earth, which is different from the diameter at the poles, and the difference is approximately 50 kilometers if I consider the diameter, and if I consider the radius, it is approximately 25 kilometers. What does it mean? I cannot assume it to be a sphere. I should consider some other shape for that, and appropriate shape is the oblate spheroid or ellipsoid. So next is Earth shape also changes because of the earthquakes, volcanoes, and any other natural hazard. So how does it matter? Suppose it is happening in some other country, how does it make a sense to my country? The thing is that the way we are defining our reference system for the whole Earth, that will make a difference in the center of mass of the Earth, or what we call as geocenter. So geocenter will be slightly shifted. So I need to observe each and every such variation that will be created by earthquakes or maybe volcanoes and so on, and other natural hazards which we cannot control. Okay, what about the other things? So other things are Earth movement. Okay, so Earth spins at its own axis, that is we call it daily motion or diurnal motion. Secondly, we also have annual motion. So Earth revolves around the sun, what we call orbiting of the Earth around the sun. Third thing is that Earth's axis wobbles while spinning. What does it mean? Let us say this is the axis of the Earth and it is wobbling, and so we have the rotation like this. That means it is spinning every day, but at the same time it is doing like that. But although the cycle of this rotation is very long, approximately 26,000 years. What's the problem? Why should we consider it? The reason is, since we are defining again the 3D reference frame and system for a surface like Earth, and hence I have to locate my 3D position with respect to time. Why? Because Earth is spinning So if I want to locate a position that is 3D in nature, I can say at time t1 it has x1, y1, z1 position. At time t2 it will have x2, y2, z2 position. And because of that, I can always say with respect to time the position of the Earth's surface is changing, or maybe my location itself is changing with time. So I need to locate the 3D position with time, and hence I need to consider all the motions of the Earth. Problem is becoming very complicated. It's very complicated. Why? Because earlier we realized that in classical survey we are not bothering the time at all. We are just taking arbitrary reference system and we started our work, and we are trying to combine all together now. But surprisingly, there are two things. The first thing is that if I consider only 2 points on the surface of the Earth, and with respect to time I know that these positions are going to change, but their relative difference in length and relative difference in direction, that is azimuth, is not going to change. So does it give me a facility here? Yes, in fact, I need not to consider the time if I calculate the difference of two positions on the surface of the Earth. Well, with this idea, let us try to understand that what we can do. Okay, so Earth as an oblate spheroid, as we have seen in this thing. So let us assume that Earth is looking like that, an apple. In apple fruit, if I remove the root of the fruit, which is shown in the figure, and the leaf, which is also shown here, so if you can imagine that Earth is somehow appearing flat, or this apple is flat from the top and slightly bulging from the middle part, and what we call as equator for the Earth. So flat from the poles, bulging out at the center part. Okay, so let us see how can we define the position on this planet, which is bulging out and flat at the top. So what is desired for positioning? Since we are considering the whole planet, or the complete surface of the planet as a one unit, I need to define a simplified and basic 3D model for the Earth. And if I can define that, I can write some mathematical equations. What will happen? I will have an advantage that, let's say, if I write an equation of ellipsoid, I will have x square by a square plus y square by b square plus z square by c square is equal to 1. I want to observe a point, let's say x, y, z, or x1, y1, z1. I can find out whether this point lies exactly on this model, that is ellipsoid, or it is lying below the ellipsoid surface, or it is lying somewhere else, maybe very close to the center of the Earth. Now that is very good approach. I really like it. There is a problem. Problem is how to fit such kind of ellipsoidal surface to this Earth. Okay, so there are two approaches, not of fitting this ellipsoid, but to find out the overall reference system for the Earth. So that once we establish a reference system, we can establish some reference figure, and using those reference figure and reference system, I can measure the 3D coordinates simultaneously. So let us see, there are two approaches. So first is gravimetric approach, that says that define a best fit geoid, that is equipotential surface of equal gravity values. First determine gravity values on the surface of the Earth, and let us fit a surface which is the best fitting surface through those gravity values. Good approach, because it is going to solve all the problems. If I measure the xy as well as gravity direction, I can do the 3D surveys the way I want. But there is another approach called define a best fit ellipsoid, that is called geometric approach. That means forget the gravity values, but just look for geometric characteristics of the Earth, and accordingly let us fit some kind of geometric shape to this planet. Let us see. So this is my geometric approach. So this is regional ellipsoid. There is some region on the Earth, and if I observe that surface with the help of some technique, so I can fit a surface like this to that region, and because of that I have a regional ellipsoid where the center of the ellipsoid is not the geocenter, or they have their difference which are quite long in hundreds of meters, but does not matter because that ellipsoid is serving the purpose of that regional area, or I can say small continent. Now let us see, these are the ABCD. So I can say AB are my two times semi-major axis, and EF is my 2 times semi-minor axis. This is the axis which is not matching with the axis of the Earth itself, the rotation axis. But yes, they are quite near, because the rotation axis of the Earth will remain almost same even if I fit different ellipsoid. So there will be slight difference between the regional ellipsoid and global ellipsoid that we are going to know in coming slides. Well, so what are the problems in geometric approach and the gravimetric approach? So let us go by the gravimetric approach. So that is the shape of the geoid. If I observe the Earth from a satellite, since we are observing the gravity values from the satellite, now we come to know recently, last 30 years back, that this is the shape of the Earth. This is the geoid shape, not the geometric shape. Geoid shape means if I try to draw potential values or the gravity potential values of each and every point, that is xy, and on top of that I am putting the gravity value, I will get this kind of shape. And hence I realized that it is not only difficult, it is almost impossible to fit a geoid that is unique in nature and that can serve as a single surface for the whole planet. Very difficult, because you can see there are two reasons. First of all, the geoid itself is very irregular in nature. Secondly, if you look, there are some sea surface, there are some land. So we can see that here on the right hand side of the screen there is a blue patch which is deeper, that is a deep sea. On the left hand side on this figure there is a blue patch, but still it is shallower. So now I have realized that there are some deep valleys in the sea, and there are some other seas there are shallow valleys, or there is no valley at all. I want to establish the MSL for one country, or unique MSL. So what are the problems possible? So let us look into that. So first is the analytical model or the mathematical equation to this surface is not possible, because in case of mathematical surface, what I need to do, I need to put some kind of contour problem, or maybe 3D contour, or maybe a 3D surface, and that surface should be of equipotential nature. We're quite difficult to fit across this particular shape. Let us see, we have devised a different approach. We will average the ocean surfaces or the level of ocean surfaces. I will create a level which will be uniquely defined. So what our earlier scientists did, they went to the sea surface and they tried to observe what is the level of the variation of sea. So they realized that over a 19 years of period, sea level varies, and they observe it. So that particular country, they have defined one MSL. Now that country is having a deep valley near to the sea coast. Because of that, the effect of tides are a little less. Let's take another country where again I am trying to do the same exercise over a period of 19 years, and there we realize that the effect of the sea tides are more because there is no valley. And eventually it happened at two countries we have different levels, and I am saying that this is my mean sea level, and my friend in another country is saying this is my mean sea level. Okay, then we started our survey. So we have assumed that yes, there are some surfaces which are equipotential in nature, and since there is water surface which is uniquely defined, it always follow the gravity direction, it always indicate the value of gravity at each and every point. Third thing, they indicate the same level of gravity value across the whole water surface. So one surface is passing through like this, another surface passing through like this, and both surfaces are parallel to each other, but they are quite different in heights, and that is why we call the local geoid for one country and another local geoid for other country. Okay, so this is the idea here. Now as I said that there are various factors like ocean currents, winds, seabed topography, tides, temperature, etc. They keep on varying, and hence these also decides the different levels of equipotential surface. So one surface is like this, curvilinear, another is parallel to this, and so we have local geoids in each and every country. It is shown here in this thing. Let us say there is a terrain shown in the green color, and if I fit the average surface through all the oceans, I will get the global geoid represented by G0, which is firm red line here. Now if I have the true geoid, which as I said, it is very irregular, and in the last picture I have already shown it, the true geoid. So let us say true geoid is also there. Now I fit an local geoid to a country, and it is coming out to be G1, and this surface is almost parallel to the global geoid, but still it is quite different from the global geoid. Secondly, I have local geoid G2, which is again for another country, but it is quite different from G1 as well as G0. So hence we end up with the different level surfaces for different countries. Okay, so that was the problem with the gravimetric approach. Let us come to the geometric approach. Geometric approach says that let us fit an ellipsoid, which is a geometric figure, on the given surface of the earth. Okay, and we have already discussed that we have some regional ellipsoids which are already fulfilling the local purposes of a particular continent or particular country or particular region. Well, so these ellipsoids were fitted using two-dimensional data and one-dimensional vertical data. Well, again, that is kind of compromise they did, but that was the only solution possible in those days. Fine, and they fitted the regional ellipsoids, and that is appropriate for a region. And for example, in 1830, during the British period, some Everest ellipsoid was fitted, and North American datum, which is done in 1927. Well, in Britain, Airy 1830 again, and Australia, Australian National in 1966, Egypt, Helmut, Russia, Krevsky, 1940, and South America, it's called South American, which was done in 1966. Well, so regional ellipsoid is not the best fit to Earth, and that is the regional ellipsoid. So what is desired here? I should fit a global ellipsoid, and that global ellipsoid should be called as mean Earth ellipsoid. And the idea is this geometric approach should be such a approach that it should be representing the approximately at least the geoid surface of the earth. And so let us imagine something where I am saying that let us fit a surface around the surface of earth that is a geometric shape, what we call as ellipsoid, but at the same time it is very close to the geoid, so that it can fulfill two purposes. First purpose is it is a geometric in shape, so I can use it mathematically. Remember, I call it, if I take a point xyz, I can find out whether it is lying above the surface or below the surface, or where it is exactly located with respect to the mathematical surface. And second is that since geometric shape will be very close to the geoid, I can always use it as a replacement to the geoid. That means even if I can measure the height with respect to this surface, but still I can be confident enough that I am doing the measurement of vertical heights approximately in the direction of gravity. And with this idea, the concept of mean Earth ellipsoid came into picture. Okay, so let us go ahead. So let us see that EF is my rotation axis. So I can say there is a global ellipsoid shown by black color in firm line. Now, what about the reference system? So we will now understand what do we mean by the reference system, reference frame and coordinate systems that is required for the surface of the earth, where I say that there are three orthogonally oriented axes at some origin. So let's say origin is given by x0, y0, z0 here, and x, y, z is showing three orthogonal axes. Well, it has a specific origin. Each axis is indicated by a unit vector. So if I take a vector of length L and divide by magnitude, then I will get a unit vector for that vector L. Now, if I take the cross product of these two axes, that means since they are orthogonally located, that means they are oriented at 90 degree mutually to each other. So if I take the x dot x cross y cross product of two axes, I should get the third one, which means x cross y equal to z, z cross x equal to y, and y cross z equal to x. You can just draw a cyclic order on a circle x, y, z, and you can do it. Well, if this property is fulfilled, I call them as a three mutually orthogonal axes. Well, so position of origin and orientation of axis can be defined with time. So now, since we have said that we are considering two kind of systems where one is dependent on the time, that means one is independent of time. Okay, there is nothing called independent and dependent of time. Well, so just try to understand What do we mean by that? Okay, the first thing is that, as I told earlier, that if I want to calculate the position of 2 points on the surface of the earth, I need not to consider the rotation of the earth or the movements of earth, because it is uniform for both the points, and as a result I can assume a reference system which is unique and same for both the points. Because of that, now what will happen? Let us see that there is a reference system which is rotating with the earth and that is attached to the earth. So because of that attachment, it is also rotating with the earth. That means there are 2 points which are rotating with some speed because of the earth rotation. At the same speed, the reference system which is attached to the earth is also rotating, and because of that, such kind of system can be used in order to locate 2 points on the surface of the earth, or locate many points. Why not? Well, that's the idea here, and such frames are, or such reference systems are called non-inertial reference system. Okay, what about the other type of reference system? The other type of reference system does not rotate with earth, and such systems are called inertial reference system. We will talk about inertial reference system later in other modules, but here we will work with the non-inertial reference system only. It's called International Terrestrial Reference System, ITRS. Well, reference system is a conceptualization, or is a concept, it's idealization. Fine. Now if I want to define something called reference frame, or in other words datum, I need to understand that if I try to realize the reference system, it is called reference frame. So in other words, I can say the realization of the reference system is called reference frame. So what do you mean by realization? Okay, let us say that you are observing some points on the surface of the earth, and using those observations you are trying to fit, or you are trying to find out a reference frame or a reference system. What does it mean? So you are trying to find out where is the origin of the reference system and where is the 3 orthogonal axes are oriented. So moment you realize this thing, or you determine this thing, the definition what we got in mathematical terms, that will be called reference frame. Okay, so as I told that ITRS, it is a reference system, that is a kind of conceptualization, that is a kind of idealization of our concepts. But at the same time, if I call it ITRF, International Terrestrial Reference Frame, it is a realization of ITRS. Well, I hope that you will understand this thing gradually as we go along this lecture or this module. So now you can imagine a rigid body. A rigid body is like maybe this body. This is a kind of remote control. It is a rigid body because with respect to time, it is not changing its shape. So now I can imagine a reference system which is non-inertial, that is, it is attached with that like this. And now if this body is moving this way, for example, so my reference system is also moving like that. So if I want to locate this point and another button, so I can always locate these 2 buttons with respect to this coordinate system or this reference system, because this reference system or reference frame itself is moving with this device, and these 2 points will remain consistent always with respect to this reference system, provided this body is a rigid body. So here we make an assumption that earth is a rigid body for some time. That means if there are some natural hazards or some volcanoes or earthquakes, whatever is there, we take care of them, we consider them, account for them, and then we again find out what's the real shape, what is the changed shape, modified shape, and based on that we will change the definition of origin of the reference system and coordinate axes. So this kind of arrangement we always consider, and then we say that let us assume earth is a rigid body. Well, now let us see there is a reference system or a reference frame xyz with origin at x0, y0, z0. So let us fit a reference ellipsoid to that surface where it is centered at the origin of reference frame. Okay, so I call it equatorial plane, which is shown by a green circle here. Fine, and this is my rotation axis, and rotation axis is cutting at north pole and south pole, And remember that if I fit the geocentric system, that means the origin at geocenter of the earth, and the rotation axis is completely aligned with this thing, I can understand that it can be a global system. That is rotation axis, and that is semi-major axis A and B. We have already defined it. Now we have already talked about non-inertial reference frames. So the non-inertial reference frame for the earth can be located at the geocenter, that is the center of mass of the earth, or it can be non-geocentric, or what we call as geodetic. Well, in case of geocentric system, we have the origin at the center of mass of the earth, geocenter. Z-axis is towards the average value of earth rotation axis. I call that is a wobbling, and whatever motions are happening with the rotation axis of the earth, I am taking the average value with respect to some time in past. So using that average value, today I define that average value is my mean rotation axis value, and I will use for this moment. Let's say after 1 year, this average will again change. So I will update myself with the new information. That is the idea here. X-axis towards the point of 0 longitude, and which is very close to the Greenwich meridian, but not exactly at Greenwich meridian. We'll see why is it so. Well, and Y-axis is forming a right-handed coordinate system with X and Z. Okay, datum I call, since it is a geocentric system, I call it the datum as geocentric datum. Okay, so I can fit ellipsoid to this XYZ system, and that will be a geocentric ellipsoid. Well, coming to the geodetic terrestrial reference frame, or geodetic or non-geocentric, they are same meaning. So origin is the center of reference ellipsoid. Remember, it is not the geocenter, or rather the center of ellipsoid does not match with the geocenter of the earth. So the W axis, we call it UV-W axis. So W axis towards the semi-minor axis of reference ellipsoid. U axis is towards the point of 0 longitude and 0 latitude on ellipsoid, and not on the geocentric system. V axis forms the right-handed coordinate system, and datum is a surface of the non-geocentric ellipsoid. Well, that is a fundamental difference between the geocentric and non-geocentric reference surfaces and terrestrial reference frames related to non-geocentric and related to geocentric. Again, let us see that what may happen if I have on the surface of the earth some reference frame. I call it the local reference frame, and origin on the user defined point on the surface of the earth. Then we have axes which are orthogonally located, and then we have defined Cartesian system. Let us see, this is my geocentric ellipsoid there, this is my equatorial plane, their rotation axis, that is north pole, south pole, and this is the rotation axis direction, or the direction of rotation of the earth. Well, this is the semi-minor axis and semi-major axes are shown. So let us go ahead. Yes, here by mistake we have written prime meridian, and it is called the meridian, not the prime meridian. Let's make a correction here. And secondly, this is the parallel of latitude, that is a circle or ellipse parallel to the equator. So this is a kind of fundamental terminology we always attach with an ellipsoid. So let us come to the geodetic terrestrial reference frame UVW, which is shown here, and there the center of mass of the earth, which is the geocenter of the earth, and at the geocenter we have a geocentric reference frame shown by X, Y and Z axis. Now let us come to the geodetic, where UVW axis are showing mutually orthogonal axes of the geodetic terrestrial reference frame, where W axis is not exactly matching with the rotation axis of the earth, but still it is very close by, and the difference between the two, it is so minimum that we have very minor rotations between the two. But what about the geocenter and the non-geocentric location of the ellipsoid? They are quite different. That means the center of ellipsoid and center of mass of the earth are away in order of 100 meters, sometimes 150 meters, on 200 meters also. It depends on how the local reference frame or the geodetic terrestrial reference frame is realized or fitted. Well, again we have seen that we have parallel of latitude and we have a geodetic meridian. Remember in the last slide we said there is a meridian, okay, and then it's called geodetic meridian in case of geodetic ellipsoid. Well, we have center of ellipsoid which is away from the geocenter and it is not the geocenter, and so we are showing here a geocentric terrestrial reference frame XYZ and geodetic terrestrial reference frame UVW here. Okay, what about the local reference frame? Well, again we are showing a geodetic reference frame and a geocentric reference frame in the screen, okay, and all the terminologies which are relevant to the two are also shown. Now let us imagine the earth by the apple surface. So on the apple surface, let us see there is a terrain, that is a terrain surface which I am trying to manifest. So point Q is there, and on the point Q, if I define a reference frame in order to work on the surface of the earth, such a frame is called local reference frame. Now at point Q as origin, I can take the measurements in the local reference frame, and then I can connect those measurements with respect to maybe geodetic system, geodetic terrestrial reference frame which is non-geocentric in nature, or I can connect the observations of a local reference frame to the geocentric reference frame that is centered at the center of the earth. And by this idea, I can always do the measurements on the local reference frame, and I can always connect those measurements to some kind of global terrestrial reference frame which can be geodetic or which can be geocentric. So that's the idea here in order to define three kind of systems. Remember, the idea of geodetic is somehow with respect to the regional surfaces or the regional observations for a country or for a region or for a continent. Geocentric is about the whole planet Earth as a single unit, and then I am trying to find out a reference system. Now coming to the coordinate system. A coordinate system is a mechanism of defining a point in a reference frame. Remember, we have already defined reference system, and we defined that realization of a reference system is a reference frame. Let us see, I want to measure a point in 3D. So how can we measure? Let's say there is a point P and there is a reference frame called XYZ, and it has an origin at point X0, Y0, Z0. Now I am showing you three measurements: ZP, that is along the Z direction, XP, and then YP, and such a system I call it Cartesian coordinate system. Well, it is well known to you, and we have been using such Cartesian system for long. Now understand that there is a point P, and I want to define the same point P with a different type of coordinate system, because it is a mechanism to define a point. So I am not changing my reference frame, I am not changing the origin of the reference frame, but at the same time I am just defining the point P in a different way. So let us look into polar coordinate system. In the polar coordinate system, I have this distance rho, which is a direct distance from the origin, and there is a point P dash, which is again the perpendicular dropped from the point P on the plane XY. And so now I measure the angle theta in the XY plane and angle alpha in the vertical plane. Let us define the distance rho, that is the distance from origin to point P, and there is a point P dash which is same here, both points are same, and now we are dropping the perpendicular from point P like this to the point P here dash here. Okay, fine. Now I am measuring two angles in case of polar coordinate system, and the first angle is measured in the XY plane from X axis like this, and another angle is alpha angle, elevation angle, which is measured perpendicular to the XY plane like this. So this is the rho, theta and alpha, which is 3D position again of point P. So this is the idea of locating point P in two ways. One, I am locating in the Cartesian way, and another way is polar or spherical coordinate system. Remember, the point is same, reference frame is same, origin of the reference frame is also same, but it is a two-way of defining a point, right? So we have other types of systems also which are very relevant for the earth. One is called ellipsoidal or geodetic coordinate system. Remember, it is not a geodetic reference frame. It is a geodetic coordinate system, and it is called lambda phi h, where h, lambda and phi are small alphabetical or the Greek letters. Then we have astronomic coordinate system, where I am using capital lambda, capital phi and capital H. Okay. And then we have projected mapping coordinate system, which is nothing but a 2D coordinate system, what we have initially criticized in this lecture, but still it is useful for many of the reasons. This is my Cartesian coordinate system for the Earth. So let's say point P, which is zoomed here. So now for point P, I am drawing ZP, XP and YP. So this is my Cartesian coordinate system, and I am defining the Cartesian coordinate system for the geodetic or geocentric reference frame for the Earth. Well, you can read it yourself that the distance xp is the distance of point P from YZ plane along x-axis and so on. Let us go for the geodetic coordinate system. What is that? So let us assume that there is a same point P and there is a geocentric system, and the geocentric system has origin O, which is geocenter. Let us drop a perpendicular from point P to the ellipsoid. We are dropping a perpendicular from point P to the ellipsoidal surface. So this is the perpendicular, and this is the intersection point of ellipsoidal surface or ellipsoid with the perpendicular line from point P. Now if I extend the line, perpendicular line to the equator, it will cut here, and now if I further extend, it will cut the rotation axis of the Earth. So this line is called ellipsoidal normal, the whole line from point P to the rotation axis, and this line is perpendicular to the ellipsoid. And if I connect the north pole, south pole and the point P1, it is called the meridian of observer, because it is passing through the observer's perpendicular projection of point P on the ellipsoid. So remember, observer's meridian is the circle or ellipse passing through the north pole, south pole and the projection of observer's point on the ellipsoid. Well, so this is called the terrestrial meridian, but remember, all these meridians, reference meridian which are defined on the surface of the Earth, or observer's meridian or any other meridian, they are called terrestrial meridian. So the OP2, if you look at, it is called equatorial axis. Well, now this angle, which is I have just shown by animation, which is the angle between the reference meridian and the observer's meridian, and this angle is lambda. Once again I repeat this thing, let us see. This is the angle between the reference meridian and the observer's meridian, and this angle is called lambda or longitude. Remember, it is called terrestrial longitude of place P with respect to some reference meridian on the surface of Earth. Okay, what about the latitude again, or terrestrial latitude? This angle, which is between equator and the line joining, that is ellipsoidal normal, if I calculate this angle, that is called phi angle or latitude or terrestrial latitude of point P1. Well, I have fixed the point P1 now in 2 dimension. That means point P1 or P, they are still same because both have lambda and phi same value. So now I define this distance which I am going to fix with respect to the ellipsoidal surface. The distance from the ellipsoid along the ellipsoidal normal to point P is called ellipsoidal height. So this is my ellipsoidal height h. Well, now I can fix the point P because h is also fixed. So point P is uniquely defined now in 3-dimensional way, and such a system is called ellipsoidal coordinate system, also called geodetic coordinate system, or sometimes called curvilinear geodetic coordinate system. So I have a geodetic longitude here lambda, geodetic latitude phi and ellipsoidal height h. Well, this kind of figures are available in the book. Let us go to the astronomic coordinate system. Here in case of astronomic coordinate system, again point P is same, but let us define the plumb line or the vertical line, that is called vertical or sometimes called plumb line in literature, that is the line of gravity passing through point P. So it is going to intersect the geocenter of the earth, and that is why we are straight away drawing it to the geocenter. Well, let us see, there is a point here, and let us see, this is a kind of a terrestrial meridian that we call astronomic meridian of the observer. Okay, what about this angle which is between the reference meridian and the astronomic meridian of the observer? And this angle is called capital lambda or astronomic longitude. Again, this angle, it's called astronomic latitude, which is between the equator and the vertical line passing through the point P. That is called astronomic latitude. Again, both are terrestrial in nature. Secondly, in case of astronomic observation, when I perform some astronomic observation, I will do some observation at certain instant. At that instant, whatever direction of rotation axis of the earth is there, I will adopt that. And as a result, we call it instantaneous north pole and instantaneous south pole, that is framed by the instantaneous rotation axis of the earth, and that becomes the z axis. Secondly, Greenwich meridian or the reference meridian is again instantaneous, because at that instant wherever I find the 0 longitude, I will say that particular meridian is my reference meridian, or I can say Greenwich meridian. But remember, it is an astronomic reference meridian. Same way, I have an instantaneous equatorial plane. Why? Because I am considering the instantaneous axis of the earth, and perpendicular to that axis I have instantaneous equatorial plane. Well, so this is called the astronomic coordinate system, but yet still it is a two-dimensional system. I need to fix the point P, and for that what I do, I'll take a geoid model. Remember, the geoid model, it could be a local geoid and it could be global geoid. Let us assume it to be global, but remember, it is decided by the mean sea level variation. Okay, say from geoid I measure this height of point P and I call it capital H, and this is height is nothing but the orthometric height. Remember, we have decided in case of plane survey or in case of classical survey, one surface called equipotential surface, and with respect to that equipotential surface we have measured some height, and similarly this height H is also the height which is measured in the direction of gravity, and this height is called orthometric height, and orthometric heights are defined with respect to the geoid. Okay, what about the role of ellipsoid here? So far we did not find any role of ellipsoid, although we are showing it here for the purpose, and the purpose is the height between the geoid model and the ellipsoid is called geoidal undulations and represented by Ng. Well, and earlier we assumed for a regional ellipsoid that a regional ellipsoid vertical line and the ellipsoidal normals are parallel, or they are basically the same, and there was some reason for that, rather it was a limitation to do that. Why? Because in those days when this concept came of ellipsoid and so on, there was no observations possible with respect to an ellipsoid. So what scientists used to do, they used to fit an ellipsoid of defined parameters. That means they have already fixed the ellipsoid. They decided that for that particular reason we are going to fit that particular ellipsoid, and for that how do they do it? They used to observe triangulation networks. They used to determine some two-dimensional points. They used to determine the vertical heights, and these vertical heights are the orthometric heights capital H. Using this one-dimensional survey for vertical and two-dimensional survey by triangulation for planimetric survey, they used to combine this data and they used to fit ellipsoid through those 3D points, and that was the idea. And since there was a problem that we did not have any global reference, what they used to do, they used to fix some stations called Laplace stations. On those Laplace stations they used to perform some astronomic observations, and using those astronomic observations they used to bring all the network of points into the global reference frame. They used to assume that the ellipsoid at one place on that region is matching with the geoid. That means the surface of the earth and ellipsoid is matching at certain point, and with this idea they used to work around. Then they used to say that now we are measuring the heights, or the heights which are orthometric in nature although, but they are being measured with respect to the ellipsoid. And that was the kind of manipulation it was in the place before the space geodesy started. So astronomical longitude is called lambda, capital lambda, astronomical latitude is capital phi, and orthometric height is capital H, and geoidal height Ng or geoidal undulations. So with the assumption H plus Ng is approximately equal to the ellipsoidal height, because we assume that ellipsoid and the ellipsoidal normal and the orthometric height or the vertical line are approximately close to each other. And with this assumption, I can find out the Ng, value of Ng or value of H if I know the Ng. And since there was no Ng available to earlier scientists, they used to assume Ng equal to 0 at one point on the surface of the earth. So the term Ng is called geoidal height or geoidal undulation. So it is called absolute undulation if I take the difference between the reference ellipsoid and mean earth ellipsoid. It is called relative undulations if I take a difference of reference ellipsoid to the local geoid. So that is the idea of the astronomic coordinate system. So let us conclude all the terrestrial reference system. So we have terrestrial reference frame and coordinate systems like this. We have coordinate system, Cartesian coordinate system, polar coordinate system, geodetic coordinate system, and astronomic coordinate system. And we have explained that how do they measure a point. The point is same, but coordinate system is a way to measure the point. And all these Cartesian, polar, geodetic, and astronomic coordinate system are 3D in nature. At the same time, we have reference frame, we have geocentric reference frame, we have geodetic reference frame, we have local reference frame. Remember, geocentric reference frame is located at the origin, or the origin of the geocentric frame is located at the geocenter or center of mass of the earth. If a reference frame global in nature, but if it is not located at the geocenter of the earth, or it is slightly away from that, it is called geodetic reference frame. And remember, we have defined various ellipsoids also and various reference frame like Everest, Clark, NAD 27. All these are geodetic reference frame because they are particular to a continent or particular to a region, not for the complete one. Then we have a local ref frame. Local frame we need to define in order to take the observations on the surface of the earth. Well, because geodetic and geocentric reference frames, they are good for conceptualization, they are good to work around, they are good to imagine or good to calculate the values of a 3D coordinates of a point in a global reference frames for large areas, but still we need to collect observations on the surface of the earth, and for that we need to define a local reference frame. So these are basically importance of different concepts of reference frame and coordinate system. In the next lecture, we are going to perform the transformations between the coordinate system, between the reference frame, and how can we change of the geocentric reference frame. All these things we are going to learn in the next lecture. Before concluding, I can say this is my curvilinear coordinate systems, that is geodetic and astronomic, and we have to assign a coordinate system to a frame so that we can measure the coordinates in a given reference frame. Okay, now finally we can see there are some variants of reference frame and coordinate systems. For example, we have reference frame, global or terrestrial reference frame. Then we have local frames. In case of global or terrestrial frames, we call it geocentric or geodetic. In case of local reference frame, it is called topocentric and non-topocentric. Remember, if the origin lies on the surface of the earth of a local reference frame, it is called topocentric reference frame. And if origin lies somewhere above or below or somewhere else, we call it non-topocentric. So then we have variants of local reference frame like local terrestrial frame, local geodetic frame, local astronomic frame. Then we have coordinate systems, we have already explained them in detail. Then we have variants of global reference frames and coordinate systems. That means I am combining different coordinate system with different frames. So I can say global Cartesian coordinate system, I can also say geodetic Cartesian coordinate system, and so on. Well, let us conclude this lecture, and this is the reference I used, and thank you very much for being attentive. Thank you very much.